Math 31. This is a lesson on composite functions. This is an important lesson, so we'll be working with this throughout the course quite a bit in a different form. We'll talk about it more later on in terms of the chain rule, which is a big thing for calculus. But anyways, it all starts here with an understanding of what is known as composite functions. So if we were to consider these two functions, first off, f and g. F at x is 3x squared, g at x is 2x. And then take a look at this unusual diagram that we've got set up here. And what I'm going to do is, not do that. Let's try to make some sense of what we've got here. Now we've got the two functions, f at x and gx, and I'm going to take arbitrary values for x. So x is 1, x is 2, and then just a general thing for just any x value. And I'm going to take those x values and map them on to the f function. So that means that this one gets mapped onto that. And that's through the f function. And if you did do that, if you plugged in x is 1 into the f function, you'll get 3 times 1 squared, which is 3. And then do the same thing with the value of 2. 2 squared is 4. 4 times 3 is 12. And then in general, all x values will become f at x. So you're thinking, well, so what? What's that got to do with anything? Well, now we're going to go one step further. After mapping the x value into the f function, we now take that value and we map it onto the g function. So we take that value of 3, which was the range of the f function, put it into the g function, and 3 times 2 will give us 6. And then we map 12 into the g function, and we get 12 times 2 is 24. And then finally, in general, when we map the f function into the g function, we would get g at f at x. So we're substituting the f value, the f function, into the g function. And we could summarize it like this. Now, this is known as a composite function, and there's a few important things to be aware of with it. First, as I said, the range of the f function becomes the domain of the g function. And then one function is fed into the other. It's one way to look at it. So we're substituting the f function into the g function, in this case, called a composite function. Sometimes they'll refer to it as a composition, but composite is what the norm is. And it's written like this, with a little dot product sign, f at g at x. And it really does mean f at g at x. So you're substituting the g function into the f function. And this is how we typically write it, although a lot of people don't like that notation as much simply because it doesn't mean as much when you look at it. And this could also be true. We could substitute the f function into the g function. More shocking still, we could substitute the f function into itself. So the range of the f function becomes the domain of the f function. And I didn't write it, but we could go g at g at x as well. Now I don't know if this is going to help it at all, but this is another illustration of it. The x, it gets mapped into the f function through the operation of the rule of the f function. Then that value gets mapped into the g function, giving you g at f at x. Now let's take a look at an example of this. Oh, before I do that, one observation that isn't really the most meaningful thing yet. Later on it comes into play for a short while. F at negative x will give you x. And remember that this is the inverse function, f inverse. So if you substitute an inverse into the original function, you're just going to be left with x. That was really the only appropriate time to mention that. So now let's take a look at these two functions, f and g, just given to us as a series of ordered pairs. And we're asked to find f at g at x. Now what this means in more direct language is that we are substituting the g function into the f function. So before I write anything down, let me put that. The range of the g function becomes the domain of the f function. So f at g at x. And we're always starting in the inner function. Start on the inside. So we look at this one, and we start with the g function. And we can note, if you take a look at this first ordered pair, this statement would be true. G at 1 is equal to 3. Now here, 3 is the range of the g function. So now, we take that 3 value in the f function, if it exists, and we note that f at 3 is equal to 2. So I repeat again, the range of the g function becomes the domain of the f function. So this means that f at g at 1 is equal to 2. And we could keep going. The next one, and you generally don't want to keep writing that out, but 2 at 5, or 2 comma 5, means that g at 2 is equal to 5. And once we get to that point, we then go to the next function, the f function, and we note that f at 5 is equal to 1. So this would mean that f at g at 2 is equal to 1. And that's what we're looking for, because now when we indicate the entire function itself, f at g at x could be indicated with the ordered pair. The first one we did, when for an x value of 1, so when x was 1, the y value is going to be 2. So that would mean we went from x is 1, giving us a g value of 3, and then the f at 3 is equal to 2. And then the next one that we just got, when x was 2, it took us to a g value of 5 up to the f function, 2 comma 1. And this pattern would maintain. When x is 3, g at 3 is equal to 7, and then f at 7 is equal to 4. And then so on. We've got, I think, 2 more points. Stop me if you want to finish this one off. But g at 4 is 9, and then f at 9 is 3. So it would be 4 comma 3. And then the very last one, g at 5 is 11, and then f at 11 will be take you to 5. So you do this a little bit. Mostly you move on to more practical applications. Next thing, though, the algebra of composite functions. So some of you would have done this before. It gets covered in 20 a little bit. Given two functions, f at x is 3x minus 1 and g at x is x squared minus 2, we want to find, first off, g at f at x. So it would mean that we want it written in this form, the f function being substituted into the g function, which would mean, now here's your g function. Everywhere you see an x in the g function, we replace it with the f function. So instead of x squared minus 2, it becomes 3x minus 1 squared minus 2. So we substitute the f function, 3x minus 1, into the g function. Now this can be simplified if you did expand it, and whether you do or not would really depend on the question. This would be 9x squared minus 6x plus 1. So make sure you FOIL it out with care, and then that would give you 9x squared minus 6x minus 1, if my math is done correct. So you want to be careful, but it's really just algebra work. And then g at f at negative 1. Now we have a choice with this one. We've already got this worked out. So all we really have to do is substitute in the x value. I could write it like this if it made it any clearer for you. Substitute in x is negative 1 into the simplified function. So if we have it worked out already, that's all we got to do. So this is 9 minus 6 times negative 1 is plus 6 minus 1. So 9 plus 6 is 15 minus 1 is 14. So therefore g at f at negative 1 is equal to 14. Now the other way you could have done it is worked out f at negative 1 first, and then substituted it in. And we'll see that in a later example. Number 3 is f at 0. So given that we have the f function of 3x minus 1, I'm going to write that off to the side. F at x is equal to 3x minus 1. We could work out the function first, which is what, or we could substitute in first. F at 0 is equal to 3 times 0 minus 1. So that's equal to negative 1. Now keep in mind what we want is f at 0. So therefore, all we have to do now is substitute that negative 1 back in to the f function. So minus 3 minus 1 is minus 4. And we're done. Take a look at another one. Number 4 is g at x. Now g at x means that we're substituting the g function back into itself. So this would therefore be equal to g at, well, the g function is x squared minus 2. So g at x squared minus 2, a direct substitution. So we write that as x squared minus 2. Everywhere we see an x, we replace it with x squared minus 2 squared, and then minus 2. Now I will expand this one. You don't always have to, but this would be x to the 4 minus 4x squared, if you FOILed it, and then plus 4 minus 2. So that would therefore be equal to x to the 4 minus 4x squared plus 2. And that would be g at x, type of thing you can do. Next question. Stop me at any point and work these ones out, as I said. Now that we have g at x, we might as well just replace in to this function. So everywhere we see an x, we replace it with 2. So 2 to the 4 minus 4 times 2 squared plus 2. And that's equal to 16 minus 2 squared is 4 times 4 is 16 plus 2 would be equal to 2. Now, that's probably enough of those. I just want to do one more question, and then the next lesson will have some applications in it, or the next video clip. Now, this is a specialty question. It's not anything that you work with too often, but there is questions like this show up in textbooks and homework a lot. So it's kind of an interesting problem. You're given f at x and you're given h at x, two different polynomial functions expressed in terms of x. And we want to find a value of function g, and that means such that, you haven't seen that before, such that f at g is equal to h. Now what that means, that we're looking for a function, the g function, that's what we want, that when we substitute it in to the f function, it'll give you h. So in other words, when we replace it into the f function, we're going to get 3x squared plus 3x plus 2. And it would be when we substitute in f, the g function, I guess I'm using a capital G now, so f at g is equal to 3x squared plus 3x plus 2. Now, the way we can solve this one is by going into this f function and actually working out what f at g would be. We just substitute in everywhere we see an x, we replace it with g, so 3g plus 5 is equal to 3x squared plus 3x plus 2, and then 3g, we subtract the 5 away and we'll get 3x squared plus 3x minus 3, and then if we divide each term by 3, we'll get g is equal to x squared plus x minus 1. So that would mean that g at x is equal to x squared plus x minus 1. And that's pretty much all you can do with that one. So I'll leave it at that. That's the basic sort of algebraic representation of it. The next exercise will be on applications of this, which is fairly important as we move through the course. Thank you.